Hello, ladies and gentlemen. It's Matthew Farrow here again, and welcome back to my space. This is a continuation of the introduction video, or again, motivation video, for a series of videos where I intend to show ways to evaluate limits of some functions without having to use something that we call the L'Hopital's rule. And in the previous video, I introduced the concepts of limits and the techniques that we use to get valid limit answers, that is, if they exist, including, again, something that we call the L'Hopital's rule, which ought to be our last resort. And in this particular video, I will continue the motivation and we'll introduce some basic tools, especially the trigonometric tools that we will need to evaluate limits of some of the functions that I talked about, where we can avoid the use of L'Hopital rule completely. So without wasting our time, let's get right into it. So in the previous video, I introduced the following techniques for solving or evaluating the limits of a function. So it means when we have a particular question, what we are supposed to do to try first is to get direct substitution of, substitute 4 directly into x, for instance, in this question, and try to see if we are going to get one of the following answers, which are the valid answers: a real number, whether 0, a negative number, a positive number, rational or irrational, or whether I will get infinity, whether positive or negative infinity. So in some other cases where I have to consider both the right limit or the left limit, one could also, get the answer that the limit does not exist. These are the only valid and acceptable limit answers. So we saw that the following are the indeterminate forms. If by direct substitution we end up getting any of the following, then it means that we cannot end there. We need to do something else to be able to get one of the valid answers. So if we look at the question 1 here, so the first thing that we ought to do is to substitute 4 for x. So it means we're going to have 4 minus 4 over square root of 4 minus 2, which is equals to 0 over 2 minus 2, and that is 0 over 0. That is an abomination. Okay, so it means we need to do something else. Then we look into our list, our toolbox. What do we need to do? So we can try factorization, we can try rationalization. Any of those two work. I know rationalization can work here because there is a radical. So I can multiply both the numerator and the denominator by the conjugate of the denominator, square root of x plus 2. That will work. Another thing that I can do, which I will do in this case, is to use factorization. I'm going to do this because it's not something common. So x minus 4, note that x minus 4 is the same thing as square root of x squared minus 2 squared. So this is a difference of 2 squares. So it means this is the limit as x approaches 4 of square root of x minus 2 times the square root of x plus 2, all over the square root of x minus 2. And of course, this cancels out, and we're left with the limit as x approaches 4 of square root of x plus 2. Now we can try the direct substitution again, and we get square root of 4 plus 2, which is 2 plus 2, and that is a valid answer, which is 4. Okay, and it's a legit limit answer. So once again, you can see that direct substitution is the first thing to do, and if direct substitution fails, that is, gives us one of the indeterminate forms, we go through all of this before even thinking about technique 6 and technique 7, which are not elementary methods of solving. In fact, for calculus 1 students, you're likely not to come across any of the the last 2 methods here. Okay, so for the second one type of question here that I have on the right, so we have the limit as x goes to 3 of 1 over x minus 1 over 3. If we substitute directly, we'll get 1 over 3 minus 1 over 3 over 9 minus 9, which is obviously 0 over 0. Another bummer. But we can solve this question by simplifying. That is the algebraic simplification. So our numerator can change into this is 3 minus x over 3x, and our denominator we can do x minus 3, x plus 3. So this is the same thing as the limit as x goes to 3 of 3 minus x over 3x times x minus 3 times x plus 3. And that is the same thing as the limit as x goes to 3 of, this cancels this and we're left with negative 1. So this is negative 1 over 3x into bracket x plus 3. And now we can try to substitute. So this gives us negative 1 over 3 times 3 into bracket 3 plus 3. So that is 9 times 6, and that is equal to negative 54. Negative 1 over 54. Yeah. So notice that all along while I am simplifying or manipulating the functions, I keep writing the limit expressions. That is what is true. If I drop at any point, if I drop the limit expression without substituting, then I have told a lie. I have written something that is not correct. All right. Then, so while, some functions can be solved, we can avoid L'Hopital's rule. There are some functions that we simply cannot use any of these simple methods. And one of the examples is this number 3. So if you plug in 0, direct substitution, you get 3 raised to power 0, 1 minus 1 over 0 minus 0, which is 0 over 0. There is nothing to factorize here to help us. There is no rationalization that can happen, and we cannot multiply by conjugates. And this is one of the reasons. This is one of the questions where L'Hopital's rule is unavoidable, and at least in the simple cases. So, and what is the L'Hopital's rule? That is what is summarized here. So, if you have limits of f of x over g of x as x approaches c, and you get something like 0 over 0 or infinity over infinity, then we can differentiate both the numerator and the denominator, because this symbol represents the derivative. So if we differentiate that, and we try doing this direct substitution again, this hopefully we get something that is legit, that is valid. And if it still gives us 0 over 0 or infinity over infinity, we keep taking the derivatives until we get a valid answer. Now, as you can see, the L'Hopital's rule requires differentiation, and differentiation is a topic that comes right after limits. And as such, this kind of question may not show up in a test that is just about limits. So for other questions, examiners would appreciate if L'Hopital's rule is avoided completely, when it can be avoided, because it is a topic that is done without, after the knowledge of derivatives. Okay, so I'm not going to, probably in the last video in this series, I'm going to talk about how to use L'Hopital's rule to solve this. And for this one, which is going to be our punchline for the kinds of questions I'm going to look at in this playlist. So this is another question where you cannot factorize anything. So you cannot use any of the first 5 methods to do this. So we can use the series expansion. Again, it is not a basic method. We can use the L'Hopital's rule we can use a geometric proof to show that this is equal to 1. So to use the L'Hopital's rule, we know that direct substitution gives us sine 0 over 0, which is 0 over 0. So it means we can use L'Hopital's rule. So that means we are going to take the derivative of sine x, that is cosine of x, and take the derivative of x, which is 1, as x approaches 0. And if we substitute now, we get cos 0 over 1, which is 1 over 1. So this is going to be our punchline, that the limit as x goes to 0 of sine x over x is equal to 1. So notice that I had to check whether the direct substitution will give me 0 over 0. If it doesn't give me 0 over 0 or infinity over infinity, I cannot go ahead and use the L'Hopital's rule, which is one of the things students fail to check before even jumping into using L'Hopital's rule when they've heard about it. So, and the following are some of the tools that we are going to need for the kind of questions that we're going to do. The Pythagorean identities, so sine squared theta plus cos squared theta equals to 1. And the remaining two, which are gotten from the first one by dividing appropriately by the either sine squared theta or cos squared theta. Then we have the even or odd formula. So sine theta and tan theta are odd functions, which means sine of negative theta is equal to negative of sine theta, while cosine of x is a positive function because cosine of negative theta is equal to cos theta. So this is odd, this is even. Then sum to product formulas will also become useful, so which we are going to see as we go through the videos in this playlist. And generally, sine k pi plus x is equals to minus 1 raised to power k sine x. So this borders on the fact that sine and cosine functions and tan function are periodic in nature. Okay, so then cos k pi plus x is equals to minus 1 raised to power k sine of x, while tan k pi plus x is just tan x, because the period of the tan function is pi. As an example, which we are going to see, sine pi plus x is equals to minus 1 raised to power 1 sine x, which is equals to negative of sine x. Okay, similar thing with cosine of pi plus x, but sine 4 pi plus x, or let's use cos, because 4 pi plus x is just equal to minus 1 raised to power 4 cosine of x, and since minus 1 raised to power 4 is positive 1, which is cosine of x, and tan anything 3 pi plus x is just equal to tan x. So that's the motivation. So the motivation, or the introduction, is what we've seen here. And if I now go back to the questions that are here, for the first one, if we put in x equals to 0, we have 1 minus cos 0, which is 0 over 0. The second one, and you cannot factorize that. The second one, you have x approaches pi. Direct substitution will give us 1 minus 1 over pi minus pi, which is also 0 over 0. The third one will also give us 0 over 0, because sine of pi is 0. The next one will give us 0 over 0. The next one will give us 0 over 0. And we cannot factorize, we cannot rationalize, we cannot do any algebraic simplification. So this can be done using the L'Hopital's rule quite all right, because they satisfy the requirement 0 over 0. But can we do this without using the L'Hopital's rule? That is what we are about to see in the forthcoming videos. So stay tuned, and you will see in the next video where we start solving each of these questions. See you in the next video. Bye.